All right, hi everyone. Today we are going to be looking at, what's up? A cat on your whiteboard. It's amazing. Did you just make that and show it to me? You're very proud? Do you need to take that home, put it on the fridge? Yeah? Okay. We have been doing so much factoring, you might be wondering, why are we doing all this? Like, why is it important? It's a very useful skill to understand a quadratic better, particularly for graphing it and understanding the different factors that built a quadratic. You would use this in business to understand your profit curves, which are built by multiplying two different factors together. Revenue per unit and number of units sold. Two different functions, multiply those together, you get a quadratic. If you can unfold those functions, you can understand each piece. So, today, we are going to be looking again at graphing f of x is equal to ax squared plus bx plus c, a quadratic given to us in standard form. This is standard form. And we're going to do so today without a table of values. We're still going to be able to find all of the intercepts and the vertex using this method, never needing a table of values. Okay? We're also going to be looking at, but in order to do this, you need to be able to understand the significance of the numbers a, b, and c, which are just constants in the equation. We've seen so many examples, different a's, different b's, different c's, and they turn into this form. F of x is equal to a, x minus r times x minus s. So we're going to understand the connection between r and s as well. Those numbers. All right, so let's get back into the world of like physics and applications in science where we might see some quadratic functions. Here's a function, f of x. It's given as negative 5x squared plus 20x plus 300. So if we were thinking about that in terms of f of x equals ax squared plus ax squared plus bx plus c. Then negative 5 is our a value, 20 is our b value, and 300 is our c value. Okay? So we want to graph this. We've been given the graph paper where we're going to do that and represent the height of this rocket. The first thing that we can do, and this is right away, is we can just put the y-intercept right onto the graph. Does anyone remember, or anyone see the trick for how we can find the y-intercept? I just did it. What did I do?
You just do it.
So what is it in this case then, if we just do it? So here's our function. Copy it out. F of x is equal to negative 5x squared plus 20x plus 300. What we are looking for is the value of the function when y equals 0. Sorry, when x equals 0. What does y equal? And one way you can find it is just by substituting in f at 0 and solving. And what you will find every time is that you get this value. Hey, Wilson, can you pull the door closed just a little bit? Thanks. This value here, the c value, is 300. And that's going to correspond to this point on the graph, 300 there. So whenever you have your c value, that always gives you the point 0, c, which in this case is 0, 300. This is the y-intercept. Make yourself a note so that you can remember this trick. You just take the c value. That's it. So we're going to go ahead and put that on. Go ahead and label your point 0, 300. There's our initial value of the rocket. Next, copy out your quadratic again. F of x is equal to negative 5x squared plus 20x plus 300. If we factor this quadratic fully, we're going to get a lot of information about this quadratic. What's my first step in factoring this quadratic? Take out that common factor, right? Yeah. Yeah, let's factor out -5. So make yourself a little note as to what you're doing. You might say like step 1, common factor. So let's use an equal sign here so we're clear what we're doing. This is equals -5 multiplied by the rest of the stuff in brackets. So my first term is just x squared, because -5 times x squared gives me -5x squared. What's the next one? Yeah.
-4.
Yeah, we'll have -4x here, because -5 times -4 will return positive 20x. And then the last one?
-60.
-60. Okay, so now we've got that common factor out. Our next step is to trinomial factor. That's with your x game. That's finding the two magic numbers. Okay. So now we're going to have, this is equal to, do we keep this -5 or do we forget about it like it never existed? We should keep it. Yeah, we keep it in this case. -5. X squared minus 4x minus 60. What are my two magic numbers that multiply to -60 and add to -4? Which one's negative? They add to -4?
Oh yeah, 4 or 10.
Yeah, so -10 and 6 are my magic numbers. So in this case, those can go directly into the brackets. X minus 10 times x plus 6. All right. So there, it is now fully factored. Hooray. Now, we can use this to find the roots of the quadratic for by solving this equation. Set the function equal to 0. F of x is equal to 0 at some point, meaning the y value will be 0. The rocket will be on the ground. And then we solve. So if I say f of x equals 0, that's like saying -5 multiplied by x minus 10 multiplied by x plus 6 is 0. So if I want to solve this equation, I have three things multiplying. -5 and the mystery number x minus 10 and the mystery number x plus 6. Is -5 equal to 0 for any value of x? -5 is a constant. It's not changing. It's always going to be -5. What value of x makes x minus 10 0? If x minus 10 equals 0, then what does x equal? X equals positive 10. Good. So some people will remember that these are sign flippers. You just change the sign and that's good. Or you just make a little linear equation, solve it, and that's the value of x for where this is 0. And this one gives us -6. Very good. So we have x plus 6 equals 0. X equals -6 just by subtracting 6 from both sides. So now what we found is f of x equals 0 when, well, this is true at f at 10 equals 0 and f at -6 equals 0. So this is the point x is 10, y is 0, and this is the point x is -6 and y is 0. So we can put those on. Here is the point 10, 0, and here is the point -6, 0. So now we can already get a pretty good visualization of this quadratic because we know y-intercept up there, we know -6, 0 over here, and we know 10, 0. So we know where this quadratic is touching all of the axes now, and all we needed to do was factor once and know to read the c value for the y-intercept. So the factored form tells you about the x-intercepts, the standard form tells you about the y-intercept. Finally, let's find the vertex this is a kind of two-step process where we're first going to find the axis of symmetry. We're going to do that by finding the midpoint of the roots. So because these quadratics are symmetrical, if I walk in this way and I walk in that way the same distance, I will find the midpoint of the whole quadratic. Visually, what's the midpoint between these two roots? Looks like 2, right? Now, sometimes with some of these quadratics, we're going to have roots that are like 1/2 or -1/4. Those ones where a was not 1 and they're trickier. Okay? In those cases, I would encourage you to just do the average. So here, to take the average, I would say, okay, I have 10 and I have -6. What I'm going to do is add those together and then divide by 2. That is taking the average of two numbers. Just take the average point between the two. And so 10 plus -6 happens to be 4, but positive. And 4 divided by 2 gives us 2. So that is to say x equals 2 is the axis of symmetry. All along the line x equals 2, the parabola is symmetrical around that line. You don't necessarily need to sketch this onto your graph, but it is useful to remember. That's where you're going to find the vertex. That's where the parabola is going to be symmetrical around. So now, in order to find the vertex, we're just going to evaluate this parabola at that height. So let's go. We're going to have f of x is equal to, and we can do this two different ways. So I'd encourage you to try this two different ways to see that it's the same. Doing things two different ways to verify that they're equivalent is a really strong strategy in math class. So here, f of x is equal to -5, x minus 10, x plus 4. So, no, it was plus 6, I'm sorry, plus 6. That was our factored quadratic. And then we also have f of x is equal to -5x squared plus 20x plus, was it 300? Yeah, 300. Okay, so we're just going to feed it this value. We're going to feed both of these this value, x is 2, and then find out what the height of the vertex is. And then we've got a great sketch of our quadratic after that point. So here, let's evaluate. F at 2 is equal to -5 multiplied by 2 squared plus 20 times 2 plus 300. So -5 times 2 squared happens to be -20. 20 times 2 happens to be 40. And 300 is just 300. 2 squared is 4. 4 times -5 is -20. So that's how I do this bit here. Be sure you don't do -10 and then -10 squared is 100. That would be a Bedmas error. One trick is that this one should always be opposite sign and half of that one when you evaluate this. You'll notice that pattern as you do this a couple times. Okay, -20 plus 40 is 20, so this is 320. So there we go. 320 when x is 2. So we can put that onto our graph here. Boop. That's the point 2, 320. But we can also evaluate over here just to verify, is that correct? So try it in your factored form and see what happens. We're going to evaluate f at 2, and that would be equal to -5 times 2 minus 10 multiplied by 2 plus 6. And another funky thing happens when we do this with factored form. Just like here where this one was half of that one and the opposite sign, and it always will be. This one here is, we're going to have -5. Do the brackets first. 2 minus 10 is -8. 2 plus 6 is 8. We're always going to see this. Those two factors having the opposite sign, but the same value. It's really neat. Okay, and then we evaluate that. So this is just a chain of multiplication. It's 5 times -8 times 8. 5 times -8 is 40. And 40 times 8 is 320. If you find that the two values you get are different, then you get to be Sherlock Holmes and go find your error. Okay, so that confirmed what we found already. Now, the last thing that we might do is just complete our sketch. I noticed that this point here is 2 away that way. So I also want to hit this point over there because it should be symmetrical. So it's going to be symmetrical around the line x equals 2. So this is the point 4, 300. That's a kind of free point that I get just from working visually. And then I'm going to go ahead and join this with a beautiful curve. Your curve should be a curve, not a line joining the different points. It wants to be flat at the top. By flat at the top, I mean it kind of comes out straight and comes down, and then we're going to aim and hit that 0 as beautifully as possible. There we go. Draw your arrow. The rocket goes down, and it's coming down towards the ground, and there it goes. Whee. Okay? So that's the path that this rocket takes through time. Okay? So, now we have a great sketch. That's our goal. Be able to do that consistently. So, next, you want to connect this back to the original situation. If I throw this marker in the air, what's going to happen next?
It's going to fall right down.
Everyone knew that because you've been living in this physics land for, 15, 16, 17 years. But this is all new. But this models the same thing that we already understand really strongly intuitively. So the more effort you put into saying, okay, what happened there and what has my math shown me? You're going to connect to things you already understand, and that's going to help back understand your math. You're going to be like, oh, I see why the math go up and then come down again. And I can reflect on the importance of these things. So the initial value, we had x was 0 and y was 300. And we have here f of x is some function of x. F of x was representing the height of the rocket, where x was time in seconds. This would be height in meters. So, what's the significance of 0 seconds, 300 meters? What does that mean in this context? So 0 seconds. Click, I start the stopwatch. Where is the rocket? It was launched from way, way high up. Pew! And it goes up and then comes down again. So then you can put in a little note to yourself. This tells us that the rocket was launched from a platform 300 meters high. Maybe a cliff or something like that, out into the ocean. All beautiful and majestic like. Okay. Our vertex was at 320. So what does that tell us? 2 seconds, 320 meters.
So that's the highest point the rocket has reached and could ever reach?
Mm-hmm. The rocket reaches its maximum height of 320 meters after 2 seconds. It's really not very exciting. You're standing on the edge of this big majestic cliff and it goes psh, up a little bit and then it just starts falling into the sea. Yeah. Okay. And then we've got roots. So our roots were -6, 0 and 10, 0. So this is -6 seconds, and this is 10 seconds. Talk to me about this root first. What does that mean in this context?
Where the rocket hit the ground.
Yeah, after 10 seconds, the rocket, I'm going to say crashes into the ocean, because my visualization is now really strong. I'm even going to change this one. Was launched from a cliff 300 meters above the ocean. There, much nicer to visualize now. But what about this minus 6 seconds? What does that mean? Does that mean minus 6 seconds the rocket was underneath the ground or started from the surface of the ocean and then comes up to meet us when we click the stopwatch?
It shows where it could have been. It's kind of like the tangent line of that parabola.
Yeah. It's kind of imaginary time. This time doesn't exist. Minus 6 seconds, the time before you start the stopwatch. What was that? We push the button on the rocket at the same time we start the stopwatch and the rocket goes up. It starts at 300 meters. This part of the curve back here, strictly speaking, isn't really part of the domain of the function. It's not a reasonable amount of time, but had we launched this rocket from down here 6 seconds earlier at a speed such that it reached 300 meters with exactly the same speed as it did when we clicked the stopwatch, it would have the same shape curve. That imaginary route is also useful for finding the vertex. We used that to find how tall the parabola would be. Okay, so the domain and range. So what is the domain and range in this situation? First, talk to me about the domain. X is real numbers or integers? X is all the real numbers. We can have fractions of a second of time. So X is of the reals, such that, what's the smallest value for X that makes sense in this context? Really? What about right when I start the stopwatch? Yeah. But negative 6 to 0 seconds doesn't really make sense, right? Like the rocket's not really flying at that time. Yeah, it starts at 0. So we would have 0 is less than or equal to x, and then the maximum value for x where this function still makes sense is 10. The position of the rocket, its speed, all that is going to change dramatically when it hits the ocean. We'd have to use a new function to model it then, probably something that is wavy and just goes up and down in the water. Okay, so there's our domain. And this, and the way we would interpret that is we would just say values from 0 seconds to 10 seconds make sense in this case. If we're looking at before 0 seconds, it doesn't make much sense, and after 10 seconds, the rocket's already touched down, so we're done. We don't need to worry about the rocket and its position anymore. We're done modeling it. How about the range? What are the values for the range that make sense here? Well, we would have y is of the reals. And what's the minimum and maximum values for y in this case that we would have? What's the minimum height that this function models for the rocket?
0.
Yeah, we can go up and we can see, yeah, we're pretty reasonable right up until about that point. This bit down here don't make sense. That's like it dives into the water or it goes into the cliff or something like that. So 0 is the minimum. And then the maximum, well, you told me that 320, which was the maximum height of the rocket, that would be the reasonable maximum. And so the physical interpretation of that is the rocket is anywhere from 0 meters high to 320 meters high. That's the meaning of the range in this case. So this puts together a lot of the different skills that we've looked at so far in this course. We're seeing function notation, we're doing substitutions with function notation, and we're interpreting domain and range and the meaning of different points in a specific context. We also used our newest algebraic strength. I've been going through your quizzes, and people are doing well with factoring, so be happy with that. It's a very important skill. We're using that skill to graph our quadratics very effectively without using a table of values. So now, go ahead and try with these two rockets yourself. I will circulate, graph these two functions. The a value of -5, you'll see this a lot in physics problems, or more accurately, -4.9. Today we're going to use -5 because it's a lot easier to work with -5, but it's basically the same thing, and that's Earth's gravity. So that's why the rocket goes up and comes down again, and why the quadratic opens downwards. One other point I wanted to mention before we go is if you're looking at supercharging your learning, think about the sketching bx plus c. That would be this line here.
What use is that? Why?
Well, it has the same y-intercept, right?
Yeah.
And it goes up at a slope of 20, like this, and this.
Okay.
So when you sketch that line, it shows you the behavior of the quadratic right at the y-intercept, so you know which direction it's sloped. Then if you know which direction it's opening, you basically can visualize the whole thing. So we can already anticipate we're going to have a negative root and a positive root. The negative root is going to be closer to the y-axis, the positive root is going to be further out. And we can see that it also shows us the velocity of that rocket immediately at launch. In fact, if we go around this quadratic with a straight line, just use this here, the slope of that line gives me its velocity. At the vertex, it's almost hovering in the air, right? It's weightless for that one moment before it starts to come down again. And the slope of this is always changing. And that slope gives you the speed. Okay.
Will you be doing velocity time graphs?
Not per se. Not in so much.
I never understand how to write these. CR,
Okay, let's turn off the video. Yeah, I will talk about that in just a second.
So that's X and Y, and that's T and G.
Come on, work. My computer is gorked. Yeah. Yeah.